All right, here is the lesson for 5.2. We're going to talk about angles, arcs, and chords. The first term we have to talk about is a central angle, and this is a really important angle. It's an angle whose vertex is at the center of our circle. So if we have our circle P over here, and it has some points on it, this angle right here, angle APB, is a central angle. But if I had a point D like this, angle ADB would not be a central angle because the vertex is not at the center. Another theorem, first theorem of the day, is the congruent circles theorem. Two circles are congruent if and only if their radii are congruent. Now, if you remember the if and only ifs from the earlier chapters, they work both ways. It's two conditionals that are both true that have been combined. So if I know I have congruent circles, then I get congruent radii. If I know I have congruent radii, I get congruent circles. And that should feel pretty sensical to us. So true or false? The circles at right are congruent because their central angles are congruent. Well, there's no way that this inside yellow circle is congruent to the outside circle because it's not the radii, they're not the central angles that make them congruent. It's based on the radii, not that central angle. Definition you don't have in your notes, but I'd like you to add is an arc. And an arc is a continuous portion of the outside of a circle. And so if I have a circle like so, from here around to here would be an arc. Now, a minor arc is an arc whose measure is less than 180, and it's named by the endpoints. So if I have a circle here with A, B, C, and D, a minor arc would be one, for example, from A to B. And we name it with the endpoints, and we put the arc symbol over it. When I go to talk about a major arc, it's an arc with a measure greater than 180, and it's named with the endpoints and one point on the arc. So an example of a major arc would be A, B, D. Or I could call that same arc ACD, but it gives me the direction and tells me which way and how far around to go. Now, a semicircle is exactly what we're used to a semicircle being. It's half a circle, but it's an arc whose measure is 180. It's named with the endpoints and one point on the arc. So in our diagram up here, if that, because it goes through the center, is my diameter, ADC would be this semicircle. And by naming the point on, it helps me see which direction I'm going. Now, arc measure is one of our ways that we can measure a circle. There are different units of measure for circles, just like there's different units of measure for length and weight and etc. But degree measure is for arcs. So arc measure is the degree measure of an arc. And the measure of a central angle is equal to the measure of its arc. So if I draw you a picture, if the central angle is 42, its degree measure of the arc is also 42. Now, some examples. If we're given a circle, first of all, remember that all of the degrees around a circle are 360, always. That holds true. So if I'm given angle AYC in this circle right here, AYC, and I want to find that. Well, all the way around, this one is 90, and so AYC plus 110 plus 90 is equal to 360. Do our subtraction, and that makes this angle here 160. So when we go through trying to classify each arc, A to B, it's less than 180, so that is a minor arc. It's the same as its central angle, so it's 110. A to C goes this direction. It is 160, and so that makes it a minor arc. ABC, A around the direction of B to C, is greater than 180. It actually measures 200. Add these two guys together. And so that is a major arc. And our final one is ACB. And while at first glance it seems the same as the last, you see when you draw it, you actually are going the other direction. So this time we need to add 160 plus 90 to get 250 for that angle, or that arc, excuse me. Some more examples. Finding x. A couple of different ways to do this problem. First thing to notice is that this angle seems to not have a measure, but if we remember our very favorite vertical angles, we know that that one is also 5x plus 5 by vertical angles. You could add all of these pieces up and get 360 and solve for x. But if we want to take an easier path, this is the diameter of the circle. So I could add those two together and get 1 to 180 and solve for x. I could also add these guys together or these guys together. We have multiple diameters and ways to add my problems together. So I'm going to take the simpler route, which is 20x plus 5x plus 5 equal to 180. Combine like terms. Subtract 5, divide by 25, and x is 7. Now this next one asks us to take a real-life problem of a pie chart and talk about it in terms of degree measure. So when we think about a pie chart, for the working class group, for part A, that is 21% of the circle. Well, 21% of our whole circle, which is 360 degrees, tells us that the angle measure and the arc measure of this section right here is 75.6 degrees. When we're asked about the arc measure of the toy group and the terrier groups together, we're going to employ angle addition, arc addition. 12% plus 16% is 28%. Find out what percentage that is of 360, multiply them together. That arc measures 100.8 degrees. So kind of in summary, we can add arcs and angles just like we've been doing. The premise behind it is that we're using our parts to whole idea. The arc measure of AC. Well, A to C is 25 plus 90. Right angles still mean right angles, so AC is 115. The arc measure of AE would be related to that central angle. This is a 90 degree based on diameter. And so if we take 90 minus 25, we get 65. And the last example with this picture is if we are looking at AEC this way around. We have our 65 that we found earlier, and this is 180 here. Add those together, and we get 245 for our arc length. arc measure, excuse me. The next topic is arc length. Now, arc length is another way to measure an arc. It'd be like using Celsius versus Fahrenheit. Arc length is talking about what fraction, what portion of the circumference is the arc. So our arc length is circumference times the fraction of the circle that we're talking about. So as a formula, circumference is pi d over 1, and then our fraction of a circle is the arc measure over 360. So for example, this arc is equal to 30. So my circumference of this circle is 12 pi, and we do want to leave stuff in exact answers. My radius is 6, diameter is 12, 12 pi. My arc measure, a measure of CD, is 30. So if I go to find arc length, I have 12 pi over 1 times 30 over 360. Now, before you reach for your calculator, I'd rather you think about handling fractions. Remember, we can cancel fractions by figuring out common factors, because 5 divided by 5 is 1, 10 divided by 10. So this is really 12 pi times 3 times 10. I just broke 30 times 10, and 1 times 36 times 10. That means that 10 divided by 10 cancels. I could rewrite this as 12 pi times 3 all over 3 times 12. I still have 36 in the bottom. I'm just writing my factors. So 3 and 3 cancel, 12 and 12 cancel. My arc length for that arc is pi units. We'll do one more example of arc length on this video. The arc length here is 46, and so my circumference is 30 pi over 1 because they're given the diameter. My portion of arc length over my whole circle. Now in this case, I'm going to cancel a little bit together. Anytime numbers end in 0, you can cancel basically a factor of 10. 3 goes into 36 12 times. So at this point, I have 46 pi over 12. 46 and 12 are both even numbers, so they have a factor of 2. And so my arc length is 23 pi over 6. And that's the end of this video.